So, alrighty. Yeah, this is Morris calling from Sydney. So, I will do some recording for tomorrow class. Hope you enjoy it. And please turn to the page of the chapter 6.3.3. So this is the S square control chart. So as can be seen from this illustrator, let me see. So this is a S square control chart. So previously we already introduced the S control chart. Now, if you like to directly to tackle the control chart about the sample variance control chart. So most quality engineer. So we'll use either R chart or the S chart to monitor process variability. Then somehow S preferable to R for as the sample size getting larger. So some practitioners recommend control chart based directly on the sample variance S square. So that is called the S square control chart. Typically S square, this statistic which does not conform to the normal distribution. Instead, it is such. It is more like log normal distribution. So the parameters for S square control chart are as follow. Can see that the upper control limit based upon the chi-square. There's a two-sided degree of freedom corresponding to n-1, and center line, as usual, will be take the grand average of the sample variance for the pass and sample points. Then the lower control chart, so also, so different the chi-square score. So where the chi-square alpha over 2, this is the right tail probability, and well, should be the 1 minus in here. This is 1 missing. Denote the upper and the lower alpha over 2 percentage points of the chi-square distribution with degree of freedom n-1. And then S square bar is an average sample variance obtained from the analysis of preliminary data. So this is collected in the phase 1. So a standard value sigma square. So sometimes if the standard value, the sigma non square, can be used in question 6.32 instead of the grand average if one were available. Note that this control chart is defined with the probability limit. Then we move to, okay, let me change the cursor. Hold on, I would like to use the other. Change the cursor like this, okay? So this is the S Schuha control chart for the individual measurement. Sometimes there are many situations in which the sample size used for process monitoring when the individual sample is only available. That is to say, the sample consists of an individual unit. So some example of this situation can be described as follows. First one, automated inspection every time, like a AOI, can be done only by one piece, and measurement technology is used. And every unit manufacturer is analyzed, so there's no basis for rational subgrouping like this. And the data became available relatively slow since the throughput is quite low. That is inconvenient to allow the sample sizes where the n is greater than 1 to accumulate before analysis. Sometimes it is too late, so the processing take a longer time than expected. So the long interval between observation will cause problems with rational subgrouping. Then this can occur quite frequently in both manufacturing and the non-manufacturing situations. The number 3, repeat measurements on the process differ only because of laboratory or analysis error, as in many chemical processes. So going to repeated measure the kind of statistic they're going to be conduct on the similar subject, however identical. So they are not identically. So actually, the subject is different from one by one. However, they exist some discrepancy in nature between the subjects. So multiple measurements are taken on the same unit of product, such as measuring oxide thickness on the top of on the surface of the wafer at the several different locations on a wafer in semiconductor manufacturing. So that's the individual we take the measurement simultaneously, however, in the different locations. In process plants, such as paper making, measurement on some parameters, such as coating thickness, across the roll. So this is the rolling plant, will differ very little and produce a standard deviation that is much too small if the objective is control coating thickness along the roll. So, and it is very difficult to form the sample subgrouping. The last one, individual measurements are very common in many transactional business and the service processes, like when you go shopping. So there's always the one service staff is corresponding to only one customer, because there's no basis for rational subgrouping. Sometimes this happens because there are large time gaps between service activity. When you go to the Louis Vuitton, you go to the Loewe or Chanel, well, the service time can only treat it as an individual observation. So in such situations, the control chart for individual units is useful. So the cumulative sum and exponentially weighted moving average control charts that will be addressed in Chapter 9 will be a better alternative in Phase 2, or when the magnitude of the shift in the process mean that is of interest quite small. We call it tiny change or tiny shift is happening and the Q sum, and the EWMA will be more appropriate than the Schuha chart. So in many applications of the individual's control chart, we use a moving range of 2 successive observations as the basis of estimating the process variability, like this. So this is called the moving range I. So currently, subtract the previous one. It's also possible to establish a moving range control chart. So in such a case, the sample size is equal to 2. So the procedure is illustrated in the following example. So like example 6.5. The mortgage loan processing unit of a bank monitoring the cost of processing loan applications. The quantity tracked is the average weekly processing costs obtained by dividing total weekly cost by the number of loans processed during the week. So the processing costs for the most recent 20 weeks are shown in table 6.6 like this. So we like to set up the individual and the moving range control charts for this data. To set up by this, so we do the subtraction to calculate the difference data. So like first one subtract the second one. This is 310 subtract 200. So actually we take the absolute value, the difference. So range cannot be negative. So this is 2 minus 1, the 22. And the 297 minus 288, this is 9. 298 minus 297 is 1, and so on and so forth. So in this case, this the 20 sample only 19. Only 19 moving range. Then we take the average is 7.79. So since n is equal to 2 observation is used. So D2 is 1.128. There's this number this number comes from the lookup table on the back when the sample size is equal to 2. So you can see that the moving range, this is for the observation, upper control limit and lower control limit. This is individual deviation and individual observation on cost and the moving range. So the control chart for individual cost value is shown in figure 6.19. So total you have have 20. So then we're going to, so A is the individual observation. Then yeah, it seems quite, yeah, it's quite in the status of the statistical control. So this is for the moving range. So the interpretation of the individual control chart is very similar to the interpretation of the ordinary X-bar chart. This is Schuhart chart. A shifted and the process mean will result in a single point or series of points that plot outside the control limits on the control chart for individuals. Sometimes a point will plot outside the control limits on both the individual chart and the moving average chart. Sometimes it is that. So if it is extrapolate outside that, so they're going to the point extrapolate the control limit, and likewise it also exhibit in the moving range chart. So it is most likely in an indication that the mean is out of control, and not an indication that both the mean and the variance of process are out of control. So cost of the processing mortgage loan application. So this is from weeks 21 until 40s. Then you can see that there's a like this. Okay, once why it is extrapolate quite in the Schuhart manner, and in the moving range. So actually there is also significant difference in some locations. So continuations of the control chart for individuals and the moving range using additional data in table 6.7 continue from the last example. So the average run length last week when I was in Taipei, I mentioned. So there's a ARL0, ARL known, and ARL1. The known, that means it's in control. So Crowder back in the 1987, there's almost the 30, well, yeah, it's a long way, 35 years ago, showed that the ARL in control of combined individuals and the moving range chart with a conventional 3 sigma limits is generally much less than, yeah, so by using the moving range than the 370 of the standard Schuha control chart. So ability of individual charts to detect small shift is quite poor. You can see that every round length we detect those. The one standard deviation, this can be considered quite moderate to small scale of mean shift. So the beta committed is so high. The average run length up to 43. That means we need to wait the almost 44 samples until the detection. We detecting the an out of control signal. So correct approach to detecting small shifts is a cumulative sum called a Q sum, or the EWMA control charting techniques, which will be described in chapter 9. So normality, more recently, still 23 years ago, Borrow, Montgomery, and Runger reported that in-control ARL is dramatically affected by non-normal data. So for this example, this is a more normal as expected. One approach for non-normal data is to determine control chart, control limits for individual control chart based on percentile of the correct underlying distribution. So use a percentile of the correct underlying. So somebody will be skeptical. Is that possible? Underlying situation is well known. So the data analysis and the data feeding can be tried. So require at least 100 or preferably 200 observations that were sufficient. So in such a case, another potential approach to dealing with non-normality, so transformation can also be useful, like a Boxen Jenkins, I'm sorry, Boxen Jenkins transformation. So this table 6.8 represents consecutive measurements on the resistivity of 25 silicon wafers after an epitaxial layers is deposited in a single wafer deposition process, like a CVD or PVDs, a chemical CVD deposition, vapor deposition, and the PVD physical vapor deposition. So it's a deposit on the surface, like a very thin film, construct an individual control chart for the process, like use a moving average. So we also take the log X, the resistivity. So the data, actually, they are not normal, apparently. A normal probability plot of resistivity measurements is shown in figure 6.22. You can see that this is probability plot. So yeah, was constructed by using Minitab, which fit the line to the point by least squares, but not the best method ever. So it is quite obviously from inspection of the normal probability plot that the normal assumption for resistivity is at best questionable. So as it will be dangerous directly apply an individual control chart to the original process data. So sometimes we don't dare to do so. So you need to do some check before we really use that. And the figure 6.22 indicates that the distribution of resistivity has a long tail to the right, is right here. And consequently, well, we would expect a log transformation or similar transformation to produce a distribution that is closer to normal. Do the transformation, the really long tail to the right here. So that the natural log of resistivity is shown in the column 3 of table 6.8, like 6.8, 6.6. So take the log, the natural log here. And the log probability plot of the natural log of resistivity is shown in the table in figure 6.23. So it can be seen clearly that the log transformation has resulted in a new variable that is more nearly approximated by a normal distribution. So you can see that. So this is almost linear. And then were the original resistivity measurements. So the last column of table 6.8 shows the moving range of the natural log of resistivity. So figure 6.24 presents the individual and the moving range control charts for the natural log of resistivity. So know that there's no indication of the outer control. So see that. Take the natural log. This is a moving edge. This is the individual. So in here we take the natural log of the x. Okay, this is the use of X bar and R chart in transactional and the service business. So I leave it to the personal reading. Okay. So this is going to be the end of the chapter 6. So we're going to move to the chapter 7.